multivariable calculus, non-homogeneous second-order differential equations. Now, if you like differential equations and we're not giving you enough in this course, there are plenty of books out there that you can purchase and learn all about differential equations painlessly. Recall how we solve homogeneous second-order linear differential equations with constant coefficients. Remember, this lesson is going to be about non-homogeneous. It's homogeneous second-order linear differential equation if it's of this form equal to 0. Okay? And remember that our strategy was to replace the second derivative, first derivative, and the function itself with r squared, r, and 1. And then we had three cases. Case 1, our quadratic equation had two real solutions, and that means our homogeneous second-order linear differential equation had a solution, a general solution of the form shown. Second case was that our quadratic equation had one unique real solution, in which case the solution to the differential equation looked like this. And the third case where the quadratic equation had two imaginary solutions, and then the solution to the differential equation is shown below there. Okay, so that's the way we did the homogeneous second-order linear differential equations, and we're going to piggyback on that with this lesson. In this lesson, we will solve non-homogeneous second-order linear differential equations with constant coefficients. So instead of equaling 0, we have an equation that looks like this. We have g of x on the end there, which is not necessarily 0. Now, step 1 is to solve the equation for when g of x is 0. This is called the complementary solution, and it will be of the form c1y1 plus c2y2, and the y1s and y2s will be different things depending on whether we get case 1, case 2, or case 3. Step 2. Solve for y sub p, called the particular solution. How we do this will be explained a little bit later in the lesson. And then step 3, write the general solution, which is the sum of the complementary and particular solutions, namely y equal y sub p plus c1y1 plus c2y2. And that will be the general solution. Now, we're not going to prove this, but we are going to show you the rationale behind the particular solution yp. We're not going to prove that, in fact, we've covered all possibilities. Let's say y and yp are two completely different solutions for our differential equation here. Okay, well then that means that if we take our equation and put y in, we get g of x. And if we take our equation and put y sub p in, we also get g of x. Therefore, if I take the first quantity on the left and subtract the second quantity on the left, then on the right I'm taking g of x minus g of x, and I'll get 0. Now here's the clever part. Collect like terms. So we have a times y double prime minus yp double prime plus b times y prime minus yp prime plus c times y minus yp. And notice then that we have a solution to the homogeneous equation, because now we've got it equal to 0, and we have a times the second derivative plus b times the first derivative plus c times the original function, which is y minus yp. This means that y minus yp is a solution for the homogeneous equation. Well, what does that mean? Well, that means that y minus yp equals our solution from either case 1, case 2, or case 3, and will be of that form. And so we've got y minus yp equaling the complementary solution, and then all we have to do is add yp to both sides. And so our general solution is y equal yp plus the complementary solution. Okay, so now we're going to show you how we're going to be finding the particular solution y sub p. Now we're going to start by assuming that y sub p is some function u1 times y1 from the complementary solution plus another function u2 times y2 from the complementary solution. We're going to make an assumption? Well, yeah, we're not going to prove why we got this or why it's the only solution, but we're going to use this to show that it does lead to a viable solution and give us some formulas to use, okay? So just bear with me. The derivative of y sub p then is this expression using the product rule twice. And then y double prime p sub p is the following expression using the product rule 4 times. Now, if this is bothersome, feel free to fast forward a little bit, but we're going to continue here. So the next step is to substitute y sub p for y in our original non-homogeneous linear second-order differential equation. And then we're going to rearrange it. And to do the rearranging takes a whole page of algebras, so I'm just going to skip to the end of that. We get u1 times this expression plus u2 times this expression plus a times this expression plus a times the derivative of that expression plus b times that same expression. Now, that a times the derivative of the quantity, you have to do some shuffling to get that. So if you do this yourself, be aware that that step's a little tricky. Okay, now here's the really cool part. See these two expressions right here? Well, y1 and y2 are independent solutions to the homogeneous differential equation. So what do these two expressions equal? Did you say 0? That's correct. So now here's what's left. Now we're going to show that there's an obvious viable solution. What we're not going to show is that it is in fact the only solution. All right. So if you take a look at that last parentheses with the b in front of it, if that were equal to 0, then the expression in the middle, u1 prime y1 plus u2 prime y2, that whole quantity prime would also be 0 because the derivative is 0, 0. And what would that leave? That would leave the first term, a times u1 prime times y1 prime plus u2 prime times y2 prime. And what would that have to equal? That expression would have to equal g of x divided by a. So we're going to use that obvious solution. And then on the next page, then we're going to solve those simultaneous equations for u1 prime and u2 prime. And again, I didn't show the steps. Feel free to get some paper and work it out for yourself if you wish. So here are the solutions for u1 prime and u2 prime when you solve those simultaneous equations. Notice that they're very similar and that the denominators are in fact identical. Now the next step is to integrate to solve for u1 and u2 and then use the formula that we assumed at the beginning that we derived all this from to write y sub p. This method of finding y sub p is called variation of parameters because u1 and u2 are used as variables, functional variables, or parameters, hence the name. Now one more little thing. In this particular text, a is always 1 because that just makes the formulas a little nicer. So in the exercises that follow, a will always be 1, which we could always get to without loss of generality anyway by dividing through by a to begin with. So if you have a different text and a is not 1, and you want to use the formulas that we're gonna use the formula without a in it because we're going to just make a equal 1, then you can just divide through by a first. And then you would just use this as your new g in the formula, and of course you've got a new b and a new c. But so in the exercises, we're actually going to use these formulas. We're not going to use the divided by a because a is always going to be 1. Okay, so you may want to jot those down, and let's move on. Are you ready for some examples? Find the particular solution y sub p for y double prime plus y equal tangent x. Now you can't find yp until you've got y1 and y2. So we're going to start by solving the corresponding homogeneous differential equation, okay, to get the complementary solution. So we use our strategy. We got r squared plus 1. That means r is plus or minus I, which is case 3. P in this case is 0 and Q is 1. So plugging in 0 for P and 1 for Q and simplifying we get C1 cosine x plus C2 sine x for our complementary solution. Now, there's y1 and y2. Okay? So moving on, we have our two formulas for u1 prime and u2 prime. Okay? So carefully, we plug in sine x for y2, cosine x for y1, and tangent x for g. And then for u1 prime, then that simplifies not so wonderfully nicely, but we end up with negative sine squared x over cosine x. All right, u2 prime comes out a little nicer. Notice that the denominator is the same as before, cosine squared plus sine squared, which is 1. That's nice. And so u2 prime is just sine x. That's going to be easy to integrate. On the next page, here's what we have for u1 prime and u2 prime. And I'm doing the hard one first. I don't know, I can do the other one in my head. So the way to integrate that is to use an identity, split it into two fractions, and then the antiderivative of cosine is sine x, and the antiderivative of secant x, you might have to look that one up. I have it memorized, is a log of the absolute value of secant x plus cosine x. Now, we don't bother with the plus c because we're just looking for a nice solution here, so just leave that out. u2 is the integral of sine x, which is even easier, and again, we don't bother with the plus c. Again, the proof of leaving that out is we're not going to look at, okay? Just trust me. All right, moving on. Here's yp, the formula for yp. We now have all our ingredients. We substitute that huge quantity for u1 times y1, which is cosine x, and then u2 is just cosine x times y2, which is sine x. Okay, and that's all they asked for in this example, the particular solution. There's our general solution, where we just take y sub p and add it to our complementary solution. So that whole thing in the blue strip would be the general solution. But they didn't ask for that, but I just thought you might want to see it. Okay? Okay, next example. Find the general solution for y double prime plus 5, y prime plus 6y equals e to the negative x. All right, so again, we first solve the homogeneous equation using our strategy of using r squared and r. That one factors into r plus 2 times r plus 3, so we get two real solutions. That's case 1. Okay, so there's our form. Substituting our negative 2 and our negative 3, we get this for the complementary solution. Okay? All right, and there's y1 and y2 then. Here are our formulas again. Plugging in carefully, we get this mess. Isn't that fun? And that actually simplifies to e to the x. Isn't that nice? That's very nice. You may want to do that on a sheet of paper or not. y2, on the other hand, notice that the denominator simplifies to negative e to the negative 5x in both cases. Simplifies also fairly nicely, and I just went ahead and integrated that. Just went ahead and integrated that. It's hard to say because it was so easy. Okay, so now we're ready for the next step. There's our formula. Y sub p, filling in from the previous page, and simplifying comes out to a rather nice expression, 1/2 e to the negative x. That's the particular solution, and we just add that on to our complementary solution and get the general solution. Okay, that was kind of painless. I like that integration, huh? Don't get used to it. Whoa. All right, this is number 6 from your worksheet. This section is not in your text, so you're going to have a worksheet. And this one looks very similar to the last one, doesn't it? All right, so let's first solve our homogeneous equation using r squared and r. And that one factors into r plus 2 squared. So we get one real solution, which is case 2. I wanted to give you an example of each type. Okay, so replacing r with negative 2, we get that complementary solution. There's y1 and y2. Here's our formulas again. And plugging in carefully for u1 prime. Ugh. Okay, and we had to use the product rule on y2 to get the derivative of y2. Isn't that fun? But it did simplify nicely. Yeah, I can't integrate that one in my head. u2 prime, plugging in, the denominator simplified to e to the negative 4x, believe it or don't. And so u2 is easy. That's just e to the x. So now we're going to have to integrate negative x e to the x to get u1. We're going to do that on the next page. Okay? Now, do you remember what method you're going to have to use for this? Hope you said integration by parts. And so we let u equal negative x and dv equal e to the x dx, because then when we take du, it equals negative 1 dx, so we kind of got rid of u. Not you, the letter u, not you, the student. I don't ever want to get rid of you. You guys are fun. And then v is just e to the x. Okay? So plugging into our parts formula, we get negative x e to the x minus negative e to the x, so that becomes plus e to the x. And so u1 is pretty easy then. It's just we're going to use negative x e to the x plus e to the x. We don't bother with the plus c. Now just to review, here are all our pieces then. u1, u2, y1, y2. And there's our formula for y sub p, the particular solution. And plugging in and simplifying, we end up with, looks like those cancel, and we just get e to the negative x. And so then we have the particular solution plus the complementary solution to give us our final general solution. All right, so here's your worksheet from the Ellis and Gullick text that I have, since this is not in your Edwards and Penny text. And so you can either stop this video and print it out, or you can go to Google Docs and look at the PowerPoint, or I will also be sending you a Word doc. And maybe I'll even post the Word doc on Google Docs for you guys. And here are the answers to the odd problems. And so you can probably guess that some of the even ones might show up on your quiz. Just saying. So now I'm going to leave you with a little tiny bit of humor. First semester. I wonder how I do this problem. Hey, I got it. She feels smart. Second semester. What is this madness? Tonk. Well, that's kind of the way I felt last year when I got to chapter 14 on vector fields. But I got it all straightened out, so hopefully your second semester will be smooth sailing. See you next time on multivariable calculus.